Thank you very much. Let's proceed to the next talk on Higgs-scalaron inflation. Professor Gorbunov.
May I start? Many thanks to organizers for inviting me to give here this talk. You see this picture. It's very difficult to concentrate on a particular part of this photo. It's actually what happens in case of Higgs inflation. Today we listen to the talk by Dmitry about inflation. So we have in hot Big Bang theory many problems, some of them like horizon problem, entropy problem, singularity problem, possible heavy relics, and initial perturbations can be explained nicely within the inflationary paradigm. So it's the idea to have a special stage before the hot Big Bang stage called inflation. And so in the standard, in the hot Big Bang theory, if you look back, you observe several regions which previously were not in causal connection between each other. Okay, and the idea to have a special almost exponential expansion stage at which the causally connected region becomes so large that actually when you look at backwards, you observe just a small part of this region. Then many problems like then the universe becomes exponentially flat, get rid of any relics, obviously because of this exponential expansion, and many other things. Okay, so it's very easy to realize this type of idea with subdynamical field. We can just introduce the constant energy density to do this. Obviously, looking at the Friedmann equation, you understand that this will help. But we should stop the inflationary stage, so it should be some dynamical ingredient which help us to do this. So the easiest thing to do is just introduce the scalar field, and then consider the situation when, well, at some moment the energy density dominate over the kinetic density and gradient density, and then looking at the equation of motion for this scalar field, you understand that actually you enter so-called slow roll solution, where the second order equation actually reduced to the first order equation. Only these two terms in the equation becomes important very quickly. And then if you look at the any power law potential, immediately understand that you can easily realize this with the field exceeding the Planck scale. Okay, that the expansion will be almost exponential, and effectively the energy density looks like constant. Okay, generically, if you look here, it's the equation of motion for the oscillator with a friction. So friction dominates in this evolution. Okay, and dynamics looks like that. You start with a large field. Then it goes slowly down, and then when the slow roll conditions becomes violated, this is the slow roll conditions. At these conditions, the evolution will be like I explained. Then it should start to oscillate here, and the universe enters more or less a normal stage, like we have in hot Big Bang theory. Okay. After that, what you need, because after exponential expansion, the universe is empty, you need to reheat the universe to transfer some part of energy of the inflaton to the particles, okay, to make the plasma. In this way, you need to introduce some kind of coupling between the inflaton and the standard model fields. Okay. Now that is great, obviously, but by like I formulated it here, it's well more or less unverifiable, because the only thing it definitely predict is that the universe is absolutely flat. Actually, up to some exponential corrections. Okay, it does not make, of course, the idea wrong, but the nice feature of this solution is that if you look at the quantum fluctuations of this inflaton field, they behave very specifically. First, the quantum fluctuation looks like the fluctuations of the massless field, and then the amplitude of this fluctuation is obviously defined by the momenta of this fluctuation. Okay, and so once the universe expands, all momenta redshifted, and so the amplitude of the fluctuations also shrinks. It happens up to the moment where the momentum becomes of the order of the expansion rate, and then it stops. Okay, the amplitude becomes constant. However, the wavelength still stretches. When the universe stops to expand exponentially, we observe that within this huge scale corresponding to this original original amplitude, you have many quantum states, actually exponentially large quantum states, instead of the first, when we start with only one quantum state, only one quantum fluctuation. Means that within this huge fluctuations, you have actually many quantum particles, which imply that it's now a kind of classical fluctuations, and these fluctuations can be used to explain, can be used as on the role of the primordial fluctuations we need to explain the inhomogeneities in the observed universe. Okay, the amplitude is fixed by the Hubble parameter at inflation, and actually the same fluctuations are produced in the gravitational sectors, in gravitational waves, and then the amplitude of these fluctuations is proportional to the Planck scale divided by the Planck mass. So if we observe this type of fluctuations, we actually measure the scale of inflation. Okay. Anyway, these perturbations can be used to explain what we observe in cosmic microwave background radiation and structure formation. And actually, the spectrum of these primordial fluctuations depends on the parameters of the inflaton model, and in this way, we can actually test the inflationary models. Say if you start with a simple example of 5 to the 4 potential is here. For the scalar field, we assume these self interactions and calculate everything. It happens that explain the anisotropy in cosmic microwave background radiation at the level of 10 to minus 5. We need to fix this only 3 parameter of this model at the level of 10 to minus 13, and in this way we match to this observation. Okay. And actually we have some predictions for the tensor perturbations as well. Okay. Now, if you look at the standard model content, we observe that there is also the very well-known Higgs field. Okay, it's scalar. And if you compare the potential, it's exactly the same way, of the same form. Okay, Higgs to the 4. However, the value of this self-coupling at the level of 10 to minus 2. So it's much huge with respect to what we have here, and it means that you can actually organize inflation with the help of the Higgs field. However, the perturbation, these quantum perturbations, will result in too large classical inhomogeneities in this universe, and this is definitely not our world. Okay. Well, actually, if you look at the constraints from cosmological observations, okay, where we consider many cosmological different observations and then try to infer the cosmological parameters. We can also infer the parameters of this scalar perturbations. Okay, and here is the tilt of this spectrum, and here is it tethered to scalar ratio. We fixed the amplitude of the scalar perturbations. However, we so far have had no any evidence for the amplitude of the perturbations, and so here is the limit. R is the ratio of the two perturbations. Okay, where? So here is the limits from constraints of this parameter space from the Planck observations, and actually similar constraints with this from other observations. So that if you look at the predictions from the power law potentials, actually pi to the 4 is somewhere here. It's already it's already excluded from this type of observations. Too large gravitational waves. Okay, too strong gravitational waves. Now, if you look here also, here is a convex and concave type of potentials. Okay, it looks like the observations prefer the concave like of potentials of this type, not this type, but this type. And well, looking at this and trying to understand whether there are any other observables which can be used to further trace the inflationary models. Well, we end up with this type of potentials, okay, and actually it's not the potential we expect from the particle physics, where we have some logarithmic corrections and they are not of this type certain. Anyway, if we just introduce to the phi to the 4 potential the non-minimal coupling between the scalar field and the curvature, it change you in the equation of motion, it change you the kinetic term. But if you replace the fields and make it canonically normalized with canonical kinetic terms, then it do this thing. It change the potential from this type to this type. Okay, and now here is the predictions for this R parameter and NS parameter, depending on the value of this parameter psi. And the predictions move towards the region which is preferred from the point of view of observations. And actually, the number here, I mean, this is this coupling is dimensionless. Okay, this number is actually not large. I mean, it's 10 to minus 3, 10 to minus 2, 10 to minus 1. It's just here. Okay, I mean, it's quite difficult actually to argue that there are no such term in nature. Okay. Well, the only thing then I should stress your attention is actually that in the standard model, as we know it, I mean, if you take the central value of the standard model parameters, then it happens that at large values of the field, of the Higgs field, the potential becomes negative. Okay, and so by making use of this trick, you cannot apply the Higgs to be the inflaton if the self-coupling is negative. However, there are still some 2-3 sigma regions where it can be positive first, and second, maybe there is some still new physics which can contribute to the running of the self-coupling and make this Higgs well positive. So well, assume for the moment that this coupling is positive, okay, or we are just 2 sigma of the central values of the top quark mass. Okay. Then we can do this trick with the Higgs field, and that was suggested by Fedor Bezrukov and Mikhail Shaposhnikov. So introduce this non-minimal coupling between the Higgs field and the scalar curvature, and well, then it's useful to to change some metric by making use of the Weyl transformation. Then we have not this type of interaction, but just the mass multiplied by the curvature at the expense of the changing of the field as well, because then the kinetic term for the Higgs field becomes non-canonical, and you should change the value of the field to change the variables, and then the kinetic term will be canonical, but the potential becomes of this form very complicated. But actually, it's flat. If you look here, independent on this function becomes flat at when this function is large. And so the form here is of this type, okay, exactly of the type I just wrote before, and it's exponentially flat, okay. Now, if you look at the effective potential for the Higgs field, it's at large value of the field exceeding Planck mass divided by the square root of psi. It's exponentially flat. Then it's actually effectively quartic, and then becomes, or it's effectively quadratic, and then it becomes quartic at the value of the field below Planck mass divided by psi. Okay. Well, if you look at this potential again, here is the flat part, okay, and the value of the field, which now depends on the ratio of the Higgs self-coupling divided by the squared non-minimal coupling, this value is fixed. It's fixed from a requirement to explain delta rho over rho at the level of 10 to minus 4. And to do this, you need to tune it in this way, okay? So this factor here is some 50 thousandths. Well, you see, with this number, we can explain everything. We don't introduce any new degrees of freedom. It's just the Higgs field. Everything is perfect. Moreover, you know, now we have after inflation, we have the energy in the Higgs field, in the standard model Higgs field, and so you don't care, you shouldn't care about the, you know, reheating, because you already have energy inside the Higgs field. The Higgs either decays to the Higgs particles or to the standard model fields, thanks to the interactions between Higgs and standard model other particles. Okay, it's Yukawa type interactions, or interactions like with top quark, and interactions with the W boson. Like for W, we have you know, the mass of W, which depends on the scalar field, which oscillate. Okay, and in this way you can you know, produce particles just through the classical oscillations. Well, actually, it's very complicated actually thing here, because if you try to calculate in this way, it happens just that actually the coupling here is somewhat suppressed by this psi, okay, and the psi is large, and so the coupling is not like exactly the standard model. It's not very small, but not very large. So you have no here the true was the enhancement in production of the particle by the external field, but still some enhancement is here. So you produce at the level of 3 number of you know, the number of degrees of freedom in one cell. And anyway, you can very roughly estimate the range for the temperature, for the reheating temperature here. And it's nice, so you can give the prediction for the parameters of the spectrum, in this case, very, very accurate, and to hope finally that you can, you know, measure these parameters and then prove that it's inflation. Okay. Well, actually, it's not the true story, because since we have this number, okay, it's a number coefficient between the self-coupling and non-zero coupling, you understand immediately that even if this coupling is small, still this number implies that the non-minimal coupling is actually large. It's much larger than 1. Okay, and so we have strong. We expect some strong coupling problem with this model. Okay, and people discuss this issue and argued that if you you know, find the regions where the strong coupling is a serious problem, when you consider the evolution of this model, okay, you never actually enter this region, so you don't need to discuss this strong coupling once you doing some predictions, for example, for cosmological parameters. Okay, unfortunately, it was not correct, because when I discussed you that we can calculate the reheating in this model looking at the time-dependent mass of the W boson, I had in mind this type of equations. However, the true equations is here, okay, and to go from this equation to another equation, I should do this gauge, and this gauge implies that the mass is constant, which is actually not. Okay. And what is main character in this play is actually the derivative of the Higgs field with respect to time. Okay, and this is the mostly, mostly oscillating part of this equation, and it's actually this oscillator which produce new particles here, and actually the production happens more or less immediately if you look at this equation, and that implies that if you look at the strong coupling regions, and here is the value of the Higgs field, here is the energy where the strong coupling serious problem. It's a bit different in the gauge sector, in scalar sector, and in gravity sector. Still, you immediately end up with the strong coupling region, and so cannot make calculations within the perturbation theory. Okay, so somehow we should restore unitarity in this model. There was an idea to do this, to introduce actually the non-minimal, to introduce actually the R² term, like we have in Stravinsky equation. Okay, so introduce a new term, which is proportional to some parameter beta here, and all the rest is the same. Okay, and then one can argue that there is a region in model parameter space where you have no strong coupling problem in the Higgs inflation. Okay, well, to show all this, it's very easily. First, we can introduce some Lagrange multiplier and auxiliary scalar, and rewrite instead of this equation, you can rewrite this one. If you write down the equation with respect to differentiation with respect to this R and L, you obtain exactly the same Lagrangian. Okay, then you can integrate out this R and rewrite the Lagrangian in this term written here. And now we look at the the scalar sector. It's here, and there are no large terms. Instead of psi here, we have actually psi² divided by beta. So if beta is larger than this number, there are no any large coupling in this sector, no problems in the scalar sector. Then you can look at the gravitational sector, again, some manipulations, Weyl transformation, and then instead of this Lagrange multiplier, we introduce the scalaron, and then we have this type of Lagrangian. Here is a normal gravitational Lagrangian and Einstein-Hilbert. We just, instead of Planck scale, we introduce 1 over the square root of 6, just to make the Lagrangian simple. Again, if you look at this part, no problem with gravitational sector again. Okay, no problem with scalar sector, and the only problem could be in gauge sector. Okay, and in gauge sector, again, we look at the gauge sector scattering of W bosons. It's useful again to make further transformation of the field of the Higgs field as a scalaron field with another replacement. And then the coupling, we have this W and the Higgs in this way. And so if we consider W scattering and exactly in the standard model, we have the contribution from the Higgs, which cancel the wrong dependence, and the amplitude behaves like momentum squared divided by the Planck mass squared. So again, we have the strong coupling and the Planck scale. That's not a problem. Okay, so in this model, the strong coupling scale moves towards the Planck mass. Now we can look at this model. In this model, we have two fields. Okay, we can look at the inflation, and here is the scalar potential, and inflation goes along this value. Okay, actually, the slope here is almost vertical. So effectively, the inflation here is one field inflation, only one important degrees of freedom here. You have no any problems, say, with either curvature. All the perturbations are adiabatic here. Okay. Instead of fixing the beta or psi squared over lambda, we fixed the sum of these two terms by this number. This number comes from the delta rho over rho. Okay, and again, if you consider the situation of beta is small, you have the Higgs inflation, you have the psi small, you have the Stravinsky inflation. Okay, so this is the two limits of this model. And in this region of model parameters, you have the Higgs inflation without any problem with strong coupling, and this corresponds to the scalaron mass in this range. Okay, it's larger than in case of Stravinsky model. Now, well, some kind of bonus here. You make the scalar potential a bit more positive because of this non-zero coupling. But anyway, let's turn to the observables. We can now calculate the observables in this model, and the first observable is related to this, perturbations. And actually, if you look at these predictions, they depends on the they actually depends on the reheating temperature. So you need to calculate reheating temperature to make accurate predictions for these numbers. Okay, it actually helps to distinguish between the Higgs inflation and R² inflation, for example. Okay, here again, what happens when reheating happens? Reheating happens at the end, when the field here start to oscillate around the minimum. Here is the Higgs. Here is here is the Higgs. Yes, here is the scalaron, and you see here is the potential. Okay, so the behavior you expect would be like this. Okay, but here you see here is a field. Okay, and when the field will fluctuate, will oscillate around this minima, if it goes upstairs. From the point of view of perturbations, it means that you have negative mass square, and this is the this is the tachyonic preheating. Okay, so now looks at this potential. It's exactly the same here. Okay, the intensity of the color means refers to the depth of the potential. So one behavior is like you have this field, stops, then bump, and then goes this way. And when it goes this way, you see it goes up and then down. Okay, and from the point of view of matter, it means that here is you have negative square mass for the perturbations, and then you very rapidly produce particles in this model. This behavior depends obviously on this trajectory. The inflation is attractive. It's attractive, and so this trajectory depends strongly on the parameters, on this psi and this beta. Okay, so by changing this psi and beta a bit, you significantly change the behavior, like from this one to this one, for example. Okay, and to this one. Okay, and here is a different behavior of the fields, obviously. And now we can look at the effective scalar potential, which is very complicated here, and try to calculate the production of particles with this very complicated scalar potential. Okay, so the main ingredients are obviously the gauge bosons, okay, and the effective mass, which looks like this very complicated thing, and also the mass of the Higgs field, okay, which looks like this. Well, it's, I mean, yes, complicated function. How we can do it numerically, and by making use of the Bogolyubov efficiency technique, calculate the number of particles produced in this way. Okay, and this is just illustration how it happens. Here is the effective mass square of the Higgs, mass squared of the W, and mass squared of the Higgs. And you see here is 0, here the positive value, here is negative value. So you can easily have the negative squared values, and that implies a huge energy transfer from the homogeneous sector to the homogeneous sector. Okay, it looks like just in this 3 different cases, 3 different choices of model parameters, and here is the behavior of this mass square, and we immediately it implies I expect some kind of huge energy transfer in these regions. Okay, and now just illustration for this case, how it looks like. This is the amount of energy in Higgs particles and in W particles in this model as a function of time. Okay, so here it's hugely grow, and here is this W. It's first than the Higgs. Okay, it's enormous number, very huge number. And just to compare, we can compare this number with energy density of the homogeneous model. Okay, so when we perform this calculation, we didn't take into account the back reaction. So we assume that we produce particles with external field, and we neglect the back reaction. Okay, so you see immediately that the production of particles is so efficient that the change in number density here is 12 orders of magnitude. Okay, so it's obvious that they have this instability. You reheat immediately. Okay, but to calculate it accurately, you need to take into account the back reaction. The back reaction account of the back reaction here is very difficult because you can't use actually neither Hartree-Fock approximation nor the classical field evolution because the number of particles is not large, and they are produced with very large momentum. So it's unsolved problem how to do this properly. Well, again, the situation strongly depends on the number of parameters, of the choice of these parameters. And sometimes it's very efficient. Sometimes it's not so efficient. Sometimes you need to wait for several Hubble times to reheat here. Okay. It's how the zero crossing happens, just to illustrate the main ingredients here. And this again spikes strongly depend on the value of the beta, for example. Okay, so all this region is acceptable from the point of view of solving the strong coupling problem in the Higgs inflation. Still depending on this value, you can have enormous production of particles and this tachyonic preheating or not. Okay, it's beta dependent thing. And still, it looks like that most probably we have the instant preheating in this case, and so these numbers prediction for the cosmological parameters in this model. Okay. Now to conclude, the Higgs photon inflation viable cosmological model, unique minimality. Okay, you don't need to introduce new degree of freedom to reheat the universe. You have this strong coupling problem which can be solved, for example, by introducing the R square term. Actually, in this model, you can calculate everything. The theory is that perturbative regime up to the Planck scale. There are problems with the particular calculation in case of this, tachyonic regions. But you understand that in any case it happens during the few Hubble times, so the predictions for the cosmological parameters are actually very robust. Okay, what is important here is our assumption. Our assumption that the self-coupling is positive. The Higgs self-coupling is positive, and it actually depends on the value of the standard model parameters. So that's why it's very important for this model to measure these parameters, to extract these parameters, so to compare these parameters from LHC data, for example, or to construct new colliders to measure this value accurately. Okay. Now one can try to invent other observables which could, show, which could probe you this model and allow you to understand in which region, region of parameters you work in, whether it's Higgs-like inflation or R-square-like inflation. Okay, and it's again depends on the reheating temperature, and actually you can suggest other things like gravitational waves. You see, in case of this almost tachyonic preheating, you produce particles immediately. Okay, many particles, and this is not thermal production, so you produce gravitational waves here also. Okay. However, these gravitational waves are very, short wavelength. At the same time, in the case of Stravinsky model, for example, where you have very long scalar stage, and only then you reheat the universe, you have effectively the dust-like stage in the universe expansion. During this dust-like stage, the perturbations of the matter perturbations here is scalar perturbations, photon perturbations. They grow and can form structures like clumps or protohalos, which later disappears after reheating. However, these structures can also, during formation of the structures and evolution of the structures and evaporation of the structures, you produce gravitational waves. And so you can calculate them and predict the, the gravitational wave spectra coming not from, again, this is not the spectra from inflation. Post-inflationary stage, and this is the way how you can test this model. Okay, thank you very much.
Thank you. Questions from Zoom first. Well, no quick questions from Zoom, from the audience.
During all these events which you showed about, what happens with entropy?
Entropy actually is produced in this model once you produce particles. Okay? So the entropy here is very simple. Yeah, just particles. Yeah,
One more question.
Could you show slide 32 or 27?
This one?
Yes, this one.
Yes.
When you represent some contours,
yes,
there are some, let us say, something like oscillator behavior of these contours. Is it? No, not this. I mean this. I mean, yes. I mean the top high. Yes. Here.
This?
No. Okay, but yes, sometimes they are oscillating. Is it physical behavior of these functions or it's technical ones?
I think it's technical. I mean, here is more accurate.
Yes. Because people ask me to come back, to ask me to show
this one.
This one.
Yes.
So, but
no, it's technical.
Because it has to be smooth. It's,
yes. It's true. If you look here, it's also very like some glue in some parts. Yes. No, of course, it should be smooth. Yes. This behavior is not. I mean, it's all. I mean, this one is very. It goes like this one. Okay. But of course, it also. I mean, smooth. If you look at here, it's also this type. Okay.
Yes, understood. But probably discretization of some points.
Yes.
Yes. Sure. And the last question from me: to what extent are these results sensitive to the experimental value of the Higgs mass? Suppose that the Higgs mass is well above the vacuum stability bounds, say 140 GeV. How will the theory behave in that case?
No, if it's you see here, I need to start with the value of the field above the Planck scale. Okay, the self-coupling is smaller, so I mean the energy density is smaller than the Planck energy density. Still, I am working here with the field of the order of the Planck scale. Okay, so I need to be able to describe this model up to this scale. So if the self-coupling is large, I have this Landau flow between us and the Planck scale.
No. You won't have Landau flow in lambda coupling before Planck scale.
If you have a large
well, this will happen for Higgs mass over I would say 200 GeV as far as I remember.
Okay.
At lower masses, everything will be smooth, and you will.
Okay. Then if we have a larger self-coupling, then I have no problems with this negative energy density, and everything is perfectly in agreement with this picture. Okay. Look, I just changed even within the original Higgs inflation. Oh, sorry. Even in the original Higgs inflation, I mean, I can look. I fixed from the cosmological observations the ratio of this ratio. Okay, actually. So this number is from cosmological observation. I cannot change it. I cannot change it. It's already observed. Okay. But if you have a larger lambda, I have a bit larger psi. That's all. So it's okay.
So just to rephrase,
This lambda is lambda at the scale of inflation. It's not lambda present at the scale, lambda at the scale of
of
inflation.
course, but they are connected.
They're connected, yes, with the renormalization group equation. If you assume that we have just a standard model or some modification which does not touch this behavior.
So can your answer be rephrased as the fact that the minimally possible Higgs mass sitting just slightly below the vacuum stability bound is crucial for construction of the model?
No.
So the
It's-
model,
No. What you need is to have positive self-coupling at large values of the T. That's all. And to be within the perturbative regime. All the rest is not important. I mean, everything after that is okay.
well, otherwise it would be nice to see why the Higgs is so light.
No, here is just you mean why we are this corner of the? I mean,
Yes, because a large corridor for Higgs masses are allowed by perturbativity and vacuum stability.
I think I have this was this one. Well, one of the type, yes. So this is the Higgs mass. This is the top quark mass. This is the metastability. This is stability region. This is instability region, and this is not perturbativity. Yes, and we are here somewhere here. Yes, this one. Yeah. Well, it's miracle. Yeah, I agree.
Just a case.
To work to employ the Higgs installation, you need to be anywhere here. Okay, everything here is okay.
So some external reason is needed to pull the mass to its lower bound.
Yes.
Okay, thanks. We should go for a break now. We have coffee. We have a coffee break for 15 minutes. Thank you very much.